small voxel size, but you can't get down to 0. If you want to spend a lot of time, you can get into the sub-voxel. You can get into a sub-voxel range, but it's extremely long, and it's a huge, it's a 200 gig file, and you're talking spending a long time doing it. So.
Okay, welcome back. Sorry for the interruption. We had a fire alarm or 2 or 2.5, maybe 3 of them in the building, but we got that figured out, and hopefully it won't happen again. Again, sorry for the interruption.
Yeah, I know I'm kind of boring, and I'm sorry, so I'll go through this quickly and let Jackie back in. But basically, the evaluation of a part is up to you. Wherever you want to do an evaluation of a 2D part over the STL, or the voxel volume. And the voxel volume is nice when you want to fly through it, or you have multi-materials. It's good for things like pins and connectors, or different plastics. So you can actually use the same 2D image, our GD&T software, because it's accredited GD&T software, to do geometric measurements of the part. You can do it either in the voxel volume, or you can do it in the STL.
So if your part doesn't totally fit within the detector, we can also do raster tomography. So what that is you would take, in this case, we took 2 scans and then merged the 2 together into one part. So here on the left, you have your detector with 1,000 by 1,000 pixels, but with the scan done on the right, you now have an image of 2,000 by 2,000 pixels. That also can affect the resolution of your part. So you can see part A on the left was done with raster tomography and part B was not. So you can see the difference in resolution there. We also have region of interest scans. So if there's just one specific location on the part that you are looking to measure, you can do that. So how that's done is you would first do a scan of the overall part so that you can establish a coordinate system, and then do a scan specifically focusing on the region that you're looking at. Like Bob mentioned. Yeah.
When you zoom in, to a particular area, I know you mentioned I guess to say the more you kind of sort of zoom in, the more fuzzier the image will actually get.
No, that's the focal spot size. It's
Okay.
It's not on a region of interest. It's not on something like this. There's 2 different. Those are 2 different subjects.
Okay.
The focal spot is just going to give you a nice, tight, crisp beam, or a nice, tight picture going into the part. So it's like focusing a camera. Think about it as focusing a camera. You're getting a nice,
Okay.
tight focus. This region of interest, what this does, instead of trying to generate, when you want to look at, this is a Norelco razor blade, right? And these blades have to have a radius on them, and they're chemically etched. Very important. But the only way to get in there and see it is to do a high resolution scan.
Okay.
Very high, very high magnification. But like Jacqueline says, without a coordinate system, without being able to put that one separate little blade into a larger coordinate system of the entire blade head, it doesn't mean anything. You have to, in order to do evaluations or be able to measure anything worthwhile,
Okay.
to be able to see radiuses or where that is in the relationship to the rest of the part, you need to do just a quick overall scan of the part. You can create a XYZ point, 0 point, planes, cylinders. Now you can go in and you can measure things. Because the part sits in virtual, when you do a scan, it's sitting in virtual space. It's in virtual air. So the machine, nothing knows where anything is. You can't really do a quick measure. You can do a heat map overlay, a quick down and dirty overlay. but you can't really go in there and say, okay, this has got to be, I need to know if this is a 25 micron radius or not. You need to give some kind of a part.
So the slide you had before that, I think it took an image, well, right before that, and it broke it down into 4. So
Correct. Think about that. So what you do is you're doing a raster. So we're doing a raster. That's an overall in the picture.
yes,
All right. So you got an in the picture part, but you have to remember the magnification. That magnification won't be that high. But with raster tomography, when you do raster tomography, you can take this corner up here. That corner just gets put into the picture and gets rotated.
okay,
Then you move your X and Y slides over because it's coordinates, because our machines are actual CMM machines.
okay,
So we do an entire mapping of all the slides. So any slide that moves, we know exactly where it is. So we can do an exact merging of the two pictures. So we merged the next picture down here because we moved our XY slide over, and we put that into a high magnification. So that's the only thing now blowing up the detector. That quadrant right there
okay,
fills up the entire detector, whereas you might have 120, like I said, it's 120 by 124. So that's a very big overview of the part.
Yeah.
That's not a high resolution. But think about getting 124 by 124 in just one quadrant. Now you've gone to a 4-time magnification of the part.
Yeah.
Actually, it's a little bit more than that. But you get to see crisp images, you get to reconstruct it, and then when you merge the 4 pictures together, the 4 rasters together, you get a nice crisp view.
So if I'm looking for a screw hole, I can zoom in that fine
Correct.
to look and see.
You do an overview shot of your part, so you give it a coordinate system,
Okay.
and then you just go and you move it into a very, very high magnification, and you center in on the region of interest that makes sense to you.
Does that take much time?
It's 2 scans. So you got to do an overview scan, and then you got to do a secondary scan.
Okay,
So it's twice as long.
however long.
Or that would be 4 times as long.
Okay.
You know what I mean? So, yes.
Thank you.
Yeah.
Thank you.
We recently did a GR&R study on a small part with features just under 25 microns. And we had a repeatability of under 1 micron. This is on our artifact correction. So like Bob said, previously, artifacts will create distortions on your STL, so we came out with a software feature that will compensate for that. So this is the part without artifact correction. You can see the ridges on it. Those ridges are not on the physical part. So with artifact correction, you can see it gives you a much smoother picture, a much clearer picture, a better representation of what your part actually looks like. And then this is an alternate view of that. To go into our newest machine that came out, our TomoScope XS. The base machine comes with a 130 kilovolt micro focus tube. This is ideal for plastics. Your part sits on an air-bearing rotary axis. The magnifications are set up manually, so this is ideal if you are doing repeat measurements of the same part. And all of our machines come with our proprietary Werth software. So what sets this machine apart from our other CT machines is that it is a monoblock design. So this means you don't need the high voltage cables that you would on other models. Those need to be greased roughly once every 3 months. With this now, we only have maintenance once every 6 months, so that reduces your maintenance costs. It comes in 130 or 160 kilovolts microfocus tubes, so the 160 would be ideal if you're doing metals. They are both, the 160 and the 130 and the 160 have the transmission target tubes. The focal spot size is 1 micron at 6 watts of power. At 50 watts of power, you'll have a 10 micron focal spot size, and you can go up to 80 watts of power on this machine. So Werth is a unified software concept. You do everything in that one software, from the projections all the way through to the dimensional measurements. We can do real-time reconstruction of your part, and you're also able to scan multiple parts at one time if they all fit in the detector and they are physically separated from each other within the fixture. And these are some examples of parts that are ideal for the XS. We have a lot of plastic parts here. There are titanium implants, pipettes, etc. And then this is kind of a guide on what is ideal for each, for the voltage of each machine and the size of the part depending on its density.
That's a wall thickness. So if you have a part with, it's a rule of thumb, and it's a nice guideline. So if you're looking at 160 kilovolt and you want to do some of the steels and some of the ceramics, you'd be looking at someplace around the 9 millimeter, but that's wall thickness. So if you have a wall on this side and wall on this side, they're both a couple thousandths. I mean, a couple, millimeters, then you won't have to worry about it. If it's a solid block, no. But if you want to go up in voltage, you can penetrate some serious steels. Titanium works very nice. Aluminum works very nice. This machine, our TomoScope XS machine, is one of the least expensive machines on the market, probably the least for the type of ability you have at 160 kilovolts. A machine like that's going to be in the $370,000 range. Up to this point, a machine with 160 kilovolts would cost you about $600,000. So we've cut that price almost in half. And that's delivered training, setup, safety training, you name it, to your door. So it's a pretty economical system. Has limitations because you can't, obviously you're not going to be able to scan through very, very thick metals. But for some of the additive, for medical markets, for plastics, for first article, for failure analysis of certain types of medical devices, it's perfect. Plus we have a really nice little software solution for being able to clock internal threads. So some of that is very, can be tough to do.
Okay.
Questions?
Do you need any licenses, considering you do? Keep forgetting. Do you need any licenses, considering you do use X-ray?
Every state has its own regulations. Usually, states are regulated by either the Environmental Protection or a health agency. So it's usually you go through a certain set of guidelines that they have, training and things like that, and where it's going to be put. However, because the machine meets all federal and FDA regulations for a cabinet X-ray machine, we've never had a problem putting an X-ray machine into any state in the union, or Canada, or Mexico, or in the world, because actually you're probably safer standing next to an X-ray machine because the background radiation is being blocked by the lead laminate that's on the machine. So there's no additional, like Jacqueline said, PPE needed. You can put the machine. It runs on 115 volt outlet in your office. The generator takes care of the rest, and it pumps it up to 130 kilovolts, and it's all self-contained. And there's interlocks and all that. Some places you need to, you buy a certificate for a year. The states are going to want it's $150, and you're good to go. But there's just a simple set of guidelines.
Okay. And I saw one of the slides that she showed prior to, in terms of having multiple parts inside of the chamber. Yeah, this one down here in the lower right-hand corner. So are Are any of your machines capable of a continuous feed?
We do have, yes, you can put a robot in there, continuous feed or pallet changing. So it's not like you can.
Run a conveyor through it?
You can't throw it on a conveyor belt.
Okay.
You need time to be able, there are machines that can do a two-dimensional inspection. And the two-dimensional inspection is exactly that. It's for maybe porosity or for cracks. But you're not going to get, you need to be able to rotate the part around, or the source has to go around, but you need to create that 360-degree scan around the part. So on a conveyor belt, no. But you can take a robot or have a pallet changer where you can come in and change pallets. Nice thing about the individual parts is that once you write a measurement program, or you save the measurement program, we have an automatic loop function. So you can loop it through. So you can, each one of those parts will get measured the same way. So you can just loop it, and you go bang, 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 and it's very, very quick. And then why it's reconstructing, doing the measurements, the operator can be, or changing it, or it can be the robot changing it, but you can have pallet changers. But no, for true tomography, you can't just hit it from one side. No, that's fine.
So does your X-ray source rotate around the object, or does the object rotate? I mean, is it on
rotates.
Okay.
The object rotates. It's on an air-bearing rotary table, a precision air-bearing rotary table. Because again, you need to make sure that you've taken out as much wobble, as much mechanical influence on that part. So it's an very high precision air-bearing rotary table. The part rotates in 360 degrees. If you go to a hospital, the CAT machine rotates around you,
yeah.
and it creates that 360. But industrial tomography, we don't care, because we can juice up the power, and we just have to rotate. When you're doing that to a person, you can't just hit them with any old X-ray source. But the part, you can make sure you don't blow through it, because there's a dynamic of added wall thickness. If you think about a razor blade's easy to penetrate this way. But when you turn it like that, there's a dynamic involved. So there's a lot of adjustments that can automatically be done, because if you put just enough to get through here, it's not going to get through here. You put too much to get through here, it's going to blow right through this. But we have automatic software adjustments that can take care of things like that. So it's an interesting science. It's really an interesting way to inspect things in quality control. It's gaining momentum and it's gaining popularity. However, it can't do everything. It's not the end all. There's still, optical and multi-sensor systems that you're always going to need to have those for certain, like very, very large parts or very, very dense parts. It's tough to get through those.
Okay, and just one more question.
Yep, no.
Is the information in real time, and can it be shared across the world? Meaning to say, is it online?
Yeah, you mean after you do a scan?
If I have an engineer in Germany and they want to see a particular scan, I mean, would I have to? You spoke about the file size. I mean, would I have to pack it in a file and email it, or?
Depends on how much bandwidth you have. Because if you take the voxel volume and you send, because voxel volumes can become gigabyte file sizes. They can 60, 70 gigabyte file sizes. That's a lot to pass over any network. You send him the STL. If he just needs to do some measurements off the STL, megabytes. You can send that like in any type of Dropbox. You can throw it on a Dropbox. You can get it, or you can even send it over email. So it depends on how you want to send it. You can that's why working in an STL is much more efficient. Well, I'm going to say efficient. Efficient for your network to be able to pass that file back and forth in your network. When you start working in a voxel volume, you got a chunk of information that's got to go. Then you have, don't forget, you got a 60 gigabyte file here, a 70 gigabyte file. You're going to need some serious computer hardware. I mean, not too long ago, they had 6 plate servers trying to crunch these numbers. Now we can do it with, you know, the computer that comes on this machine has 2 Xeon processors, 205 gigabytes of RAM, special DMR, whatever they call it. It's quite a piece of equipment. You know, server-grade computer, and it can crunch numbers quickly. That's why we can do on the fly. As Intel gets better at giving us chips and be able to process this stuff, computer tomography is going to get, that's right, you know, where it's at, is being able to crunch the file, crunch the numbers. So, yeah. So, any other questions? Thank you so much for your time, and if you have any questions, we're upstairs. Please come and see me. I have some books on computer tomography. We'd be more than happy to hand it out. Thank you.